This is video 6 of our coverage of Chapter 2 of your computer systems book. This video continues with Section 4 of Chapter 2. We'll be going over some more examples and properties of floating point numbers and taking a look at rounding, addition, and multiplication. Let's use a tiny little 8-bit floating point representation to keep things simple. In this case, we'll use the most significant bit as the sign bit, just like with normal floating point representations. We'll use the next 4 bits for the exp field and the final 3 bits for the frac field. Because we have 4 exponent bits, we'll have a bias of 2 to the third minus 1, or 7. With this small representation, we can still use the same general format as the IEEE format and represent normalized, denormalized, and special values like zeros, not a numbers, and infinities. This slide shows the range of numbers we can represent with this tiny format. We're just looking at the positive numbers here, but you can get the idea of how the denormalized, normalized, and positive infinities, or positive infinity, is represented. Just like in larger representations, we see that the denormalized and normalized numbers distribute in the same way. Denormalized numbers are close to 0, with the normalized numbers spreading out from there to the infinities. Notice that the denormalized values are linearly separated around the zeros, while the normalized numbers cluster closer to each other the nearer they get to the denormalized range. This is the case for the standard floating point representations, single precision, double precision, and extended precision, that we went over in the last video. Let's take a look at some special properties of the IEEE encoding that have an impact on comparing floating point numbers. Comparisons work much the same as unsigned integer comparisons, but with a few things to keep in mind, and a bit of a problem with the not a number floating point representation. The first thing we must account for when comparing floating points is making sure to compare the sign bits. We don't want to accidentally say that 500 is equal to negative 500, for example. We also must remember that for the purposes of comparison, negative 0 is equal to positive 0. Now on to the not a numbers. They will be greater than any other values, but how should we compare a number with something that is not a number? Keep in mind that not a numbers are not numerically defined, so the IEEE standard states that not a numbers will compare unordered with everything including themselves. This means that any comparison with a not a number will return false, including comparing not a number with itself. So keep in mind that when coding, not a number does not equal not a number. Other than that, we're fine. Denormalized versus normalized versus infinite values will compare as expected. The basic idea of floating point addition and subtraction are pretty simple. First, we compute the exact result, then we make it fit into whatever precision we're using. If the exponent ends up too big, we overflow to positive or negative infinity. We may also need to do some rounding to fit our significand into the frac field. Since we'll be doing some rounding when we perform operations on floating point numbers, we should take a closer look at the various options open to us when rounding. This table shows some examples of various types of rounding operations. Notice that the last option, nearest even, is the default behavior that we will be using. So let's take a closer look at round to even and what it looks like for fractional values. There are a couple of advantages to using round to even that we should be aware of. First of all, it's very difficult to implement any other kind of rounding without dropping into assembly, which can be fun, but it's also time-consuming and somewhat difficult to do well. Also, any rounding option other than round to even ends up being statistically biased. This means that summing a set of positive rounded numbers will be consistently over or underestimated. So, round to even works just as you'd expect when the value is more or less than halfway between the values that you might round to. If it's less, you round down. If it's more, you round up. The interesting case is when you are exactly halfway between the possible values you want to round to. Should you round up or down in that case? The answer is that you round so that the least significant digit of the rounded number is even. Take a look at the 2 examples at the bottom of the slide. Both are halfway, but the first one will give us an even number as the least significant digit by rounding up, and the other does so by rounding down. So, what does all this look like when we're dealing with binary numbers? Well, binary numbers are even when the least significant bit is 0 and odd when it's 1. When we say halfway, we mean that the bits to the right of the rounding position are of the form 1 followed by nothing but zeros. Let's look at some examples of rounding to the nearest 1/4, which is 2 bits to the right of the binary point. In the first and second cases, we are less and more than halfway, respectively, so we just round down and up as expected. The bottom 2 examples are halfway. Note the bit patterns in red, which are of the form 1 followed by zeros. In the first case, rounding down would lead to a least significant bit of 1, meaning the result would be odd, which does not conform to the nearest even rounding that we're doing. So we need to round that one up. In the bottom example, rounding down is what leads to an even result, so that's what we do in that case. Right now, we'll take a look at the basic steps of floating point multiplication and addition, and in our next video, we'll look more in depth at exactly how the steps work with some examples. We'll start with multiplication. Remember that we first compute the exact result and then fix anything we need to fix to fit it into the precision we're using. The exact result is straightforward to calculate. The sign bit is obtained by exclusive ORing the sign bits of the operands. The significand is obtained by multiplying the significands of the other operands, and the exponent e is obtained by adding the exponents of the operands. The problems we may need to fix are next. If the significand is greater than or equal to 2, we shift m right and increment e by 1 for every bit we shift by. If the exponent ends up out of range, we overflow. And we will also need to round m, our significand, to fit into the frac field if it ends up being too long. Now on to addition. Note that we're assuming that E1 is greater than E2. First, we need to get the binary points aligned, which we can do by shifting the first significand to the left by E1 minus E2 bits. We then do a simple signed addition of the shifted M1 and M2. This gives us our values of m and our sign bit s. The exponent will simply be E1. Fixing ends up much the same as with multiplication. If m is greater than or equal to 2, we shift right and increment e. We also have to see if m is less than 1. If so, we shift m left and decrement e by however many positions we shift m by. As with multiplication, we overflow if e is out of range and round m to fit into the frac field. So that does it for this video. That's just a very, very quick look at floating point addition and multiplication, but again, we'll take a more in-depth look at what fixing looks like in our next video. So in that next and last video on floating point numbers, we'll take a closer look at floating points in C, and again, what the steps in encoding and fixing floating point numbers look like.